So thank you very much for the invitation. I'm sorry for not being in Montreal in person. And I also have to apologize because I'm not going to scale anything in this talk. These are about exact identities. Here is the thing, the Jacobi triple product. Depending on your background, you may find it a beast or a beauty. It's about a triple product of 1 plus x powers and 1 minus x powers on the left-hand side, and it's equal to this kind of sum of x to the m square. And it's something that people know in number theory and combinatorics and partitions and also the algebras. But I've never seen it honestly before I run into this from particle systems. So I'm going to prove this, show you how to prove this with particle systems, and then I'm going to tell you about a little bit of generalization. So my particle systems are actually going to be just the simplest ones you can imagine, like asymmetric exclusion and asymmetric zero range. So it's all about blocking measures of those, and I'm just going to tell you how to get to this triple product more or less. And then I'm at the end of the last couple of minutes, I'm going to introduce a couple of more models we are looking at and get some other identities. Okay, so everybody by now, I'm pretty sure, knows asymmetric simple exclusion. So it's the simplest case. I have particles jump into the right with rate p and left with rate q if they can, but there's the exclusion rule. So everybody knows this very well here. I'm going to assume that p is bigger than q, so there is an asymmetry to the right. Okay, so that's exclusion. And then that's zero range, again, asymmetric to the right. So right jump rate per edge is p, left jump rate is q, constant rate. So the jump rate over edges doesn't depend on how many particles are on the edges, and jumps always take place as long as there is somebody to jump. So again, asymmetric drift p minus q to the right, that's zero range. And so the basic question I'm going to address is, can we have blocking measures? Namely, can we have reversible stationary distributions? And I want them in product form. Now, if you have an asymmetric particle system, then usually in the translation invariant case, you do not have reversibility. So that's going to be a non-translation invariant case where you do have reversibility. And this is reversibility, of course. So the probability of a state times the rate of jump is the probability of the resulting state times the rate of jumping back. And because it's partially asymmetric, jumps left and right can go back and forth. So this notation here, omega of I plus 1, is just the state resulting after a jump. So you subtract one particle at I, you add one particle at I plus 1. So that's what happens both in zero range or exclusion after a jump. You have one less at I and one more at I plus 1. So the question is, can you satisfy a detailed balance with a product measure? And let's take a look at exclusion. So here is detailed balance again. So you want probability times rate is probability of the new state times rate back. And because it's nearest neighbor, it's really just over jumps over one edge. So I'm really just looking at jumps over one edge. If I want a product measure, then of course the only thing I can do with 0 or 1 particles is Bernoulli. So I really want a product Bernoulli, but the thing is that I allow the parameter to depend on I. So it's not translation invariant. I allow the probability of seeing a particle to depend on I, the location. So if you translate this detailed balance equation and you cancel out all the terms that you're not interested in, namely every site outside I and I plus 1, then you just really have the components of this product Bernoulli at I and I plus 1. So the only way you can have a right jump is that you have a particle at I and nothing at I plus 1. The probability of that is rho I times 1 minus rho I plus 1. The jump rate is p, and when you do the jump, then that's the new state. In this new state, the product Bernoulli gives you probability 1 minus rho I and rho I plus 1, and the rate back is q. So detailed balance tells you that this should be equal. The left-hand side should be equal to the right-hand side. And this you can easily solve and get this logistic transition from 0 to 1 in the density parameter. So you have nobody on the left, at least the probability of having a particle far on the left is going to 0, far on the right is going to 1. And you have this nice logistic transition. In fact, there is a free parameter C, which essentially pushes this curve left and right. You can have this blocking scenario anywhere left and right. This is very classical stuff. So I think the first papers about this came out with Liggett in the 70s, maybe even earlier than that. So this is well known. Let's take a look at zero range. Can you do it in zero range? And this is not new either. So there were some early papers on zero-range blocking measures. So the question is the same. Let's look at zero-range station distributions in a product form, but it's not translation invariant. Can we have a product measure here so that probability times rate is the probability of the new state times rate back? And again, since we're assuming a product measure, everything cancels out except for the edge of the jump. So if I'm looking at jumps over the edge I plus 1, then the only relevant thing is just the product of the measure at I and I plus 1. The jump rate is P, assuming that there is at least one particle. The resulting state is one less at I and one more at I plus 1. And the rate back is Q. And actually you could, if you want, put the indicator here, but since you just jumped to I plus 1, there is always at least a particle to jump. So that's the detailed balance equation. Can you solve it? Yes, you can. It's very easy to solve it. Since this should be true for every omega, you soon realize that the ratio of omega I and omega I minus 1 in the measure should be a constant, which means you're dealing with the geometric distribution. So a product geometric actually satisfies this, and that's the only thing that satisfies this. And you have again a non-translation invariant case. The parameter of your geometric will depend on location, and you have a constant which essentially pushes left and right the whole picture. So that's the zero-range product blocking measure if you want. Okay, so I'm going back to exclusion, and I'm going to explore this blocking measure a little bit more because there are some interesting features of it. The first thing I want to notice is that the probability that you don't see a particle in that blocking measure, remember we had this logistic formula for the density. That's one way of expressing it, 1 minus the parameter rho I. It turns out to be 1 over 1 plus p over q I minus c. If remember p is bigger than q, or in all of my talk p is going to be bigger than q, so there is a drift to the right. If you now take I to infinity, you see that this decays exponentially fast to 0. Whereas if you look at the probability of a particle, you can rearrange that. You take just rho I, you can rearrange that to this form. P is bigger than q, so q over p is less than 1. So if you take I to minus infinity, then again exponentially fast, this goes to 0. That means that by Borel-Cantelli, by summability of these probabilities, almost surely according to this measure, there is a rightmost hole and there is a leftmost particle. So you just have finitely many holes on the right and finitely many particles on the left. Okay? And therefore, I can define this quantity here. I'm going to count the number of holes. So eta is 0. That's when I have a contribution on this one. On my right-hand side, so on positive sides. And on negative sides, I'm going to count the number of particles. When eta is 1, I have a contribution there. I take the difference, and according to the previous line, this is almost surely finite according to my product measure. Okay? But not only that, it's actually a conserved quantity of the dynamics. So here is a typical realization, well, a random realization. I have full of particles on the right. There is a rightmost hole, this guy here at site 4. I'm completely empty on the left, so there's a leftmost particle at site -3. My conserved quantity here is 3 holes on the right minus 2 particles on the left, so it's equal to 1. And now I'm going to prove you by movie that this is actually a conserved quantity. So let's see the dynamics. What happens if this particle decides to jump? Well, you're going to have now 2 holes on the right and 1 particle on the left, and the difference is still 1. And you can easily convince yourself that whatever happens in this asymmetric simple exclusion, this quantity stays the same. It's a conserved quantity. Okay? So the state space, well, exclusion generally has state space 0, 1 to the z, but now I can actually break it down into according to the values of this conserved quantity. So first of all, I assume that there is a leftmost particle and there is a rightmost hole. And then I also assume that the conserved quantity is n. And that's giving me kind of a restricted state space of omega n. These are going to be the irreducible components of my Markov chain. And also, if I look at the union of these omegas, because this quantity is almost surely finite according to the product measure, so this non-translation invariant product blocking measure will give probability 1 on the union of these state spaces. So I essentially broken up the state space, except for 0 measure set, into these irreducible components according to the conserved quantity. Okay, so that's the first observation. The second observation is that the conserved quantity plays very nicely with shifts. So what is a shift? A shift is just moving the whole configuration one step to the left. Then, at least in my definition, it's going to be a left shift. I claim that if you shift the whole configuration to the left, the conserved quantity is decreased by 1. And again, let's do a proof by movie. So in this picture, you have 3 holes on the right and 2 particles on the left. So now I'm going to shift everything to the left. And what happens is you have 2 holes on the right and 2 particles on the left. So from 1, I decrease the conserved quantity to 0. Let's do one more shift. Now I have 2 holes on the right and 3 particles on the left. So my conserved quantity is now -1. And again, you can easily convince yourself that this will always decrease the conserved quantity by 1. So this shift operation will take me from the n subspace, the conserved quantity equals n subspace of my state space, into the one with n-1. So you have this quite nice picture that you have these irreducible components here, and the left shift is bringing you to the left of this picture, and the inverse of it, the right shift, is bringing you higher in the conserved quantity. So what do you do when you have a stationary distribution with a conserved quantity? Of course, you try to do the ergodic decomposition. You try to write this probability as the conditional probability given the conserved quantity times the distribution of the conserved quantity, just the law of total probability. And so just to abbreviate things, this conditional one is going to be nu n. So nu n is the product measure, this Bernoulli non-translation invariant product measure conditioned on the conserved quantity. And the next thing I want to do is find the coefficients, find what kind of mixture of these nu n's is the product measure. How is the product measure mixed out of these irreducible component measures, nu n's? Okay, so that's the next task. So let's do that. It's actually quite easy to do. So rho I, this was the density parameter. If you remember, this was this nice logistic transition from 0 to 1. And it's very easy to formally write out the Bernoulli distribution according to this parameter, the product Bernoulli. All you have to do is take the parameter, and on top here, I'm going to put an eta I. So if eta I is 1, then I have this probability. If eta I is 0, then I just have 1 minus this probability. So that's exactly Bernoulli. It turns out to be useful for negative sides, and for positive sides, it turns out to be useful to use this other form, which is equivalent. So these are just 2 equivalent ways of expressing the same thing. So on the right-hand side, when eta is 1, then I have 1 over this stuff, which is exactly my rho. When eta is 0, then I have 1 minus that. So it's just a way of writing mu, really. And then you can also write what the shifted state has for this probability. So shift this state and look at mu of that shifted state. All you have to do is change the I index to I plus 1. And then here comes a few lines of algebra, which I'm not going to show you due to lack of time. But with a few lines of algebra, changing this I plus 1 back into a new variable j, you end up with the following identity. Mu of tau eta is the same as mu of eta, except for a factor that includes the conserved quantity. So shifts play really well with the product measure. If you shift the state, all you get is a factor of p over q to the conserved quantity minus this constant c. So that's nice. That's something you can actually use to find out the distribution of the conserved quantity. So here is how that goes. What is the product measure? So the original all mixing together product measure probability that the conserved quantity of n-1. When you look at all states with that conserved quantity, the probability of that state. And now you say, okay, this is a sum. So I'm going to change variables. I'm going to use tau eta instead of eta. It's a 1-to-1 map. So tau is just a shift. So it's 1-to-1. So that's a new summation variable. Now I'm going to use what I learned before. I learned that n of tau eta is one less. So if n of tau eta is n-1, then n of eta is equal to n. So I know that. And I also learned in the previous slide that mu of tau eta can be expressed with mu of eta, except for this factor here that has the conserved quantity. So everything is really nice. On the left-hand side, you just realize that you just have mu of n equals to n, because you look at all states with conserved quantity n and the probability of those. and you have this factor p over q to the n minus c, so you got a nice recursion for yourself, connecting the probability n is n minus 1, the probability n is n. You can easily solve this recursion, and what you get is a discrete Gaussian. So what we learn from that is that the product logistic density transition, so the product stationary distribution, which is a reversible stationary measure, is not ergodic, it's not irreducible in the state space, but it mixes according to a Gaussian, discrete Gaussian distribution, it mixes together these irreducible components of my Markov chain, the new n's. Okay, so this is where we are so far. Okay, now combining everything together, we're actually able to give an explicit form of the new n's. So these are the guys which act on these irreducible components. And if you have a reversible measure, reversible stationary distribution, and you restrict it to an irreducible component, you still have a reversible stationary measure. So these guys are stationary reversible on the irreducible components. And you have an explicit form to them, coming essentially from the product measure and this conditioning on the conserved quantity, which has the discrete Gaussian in it. Okay, and this is the unique stationary distribution, because now we are on the irreducible component. Every state is reachable from every other state. It's a countable state space Markov chain, so everything works out very nicely. Okay, let's keep this in mind, because now I'm going to switch to zero range. So I'm going to look at zero range in the same eye, except that something is going to be fundamentally different. Nobody stopped me when I said that we have the product geometric with these parameters. But if p is bigger than q and I is bigger than the constant, then this doesn't make any sense, because this is larger than 1. What is geometric with a negative parameter? And that's not something we can make sense of. So what I'm going to do is I'm going to fix the constant at 1, and at I equals to 1, I have 1 minus something to the 0. So I have geometric with parameter 0. What is geometric with parameter 0? It's an infinite pile of particles. So fixing the constant at 1, I'm going to imagine that I have a right boundary of an infinite pile of particles at site 1, and I'm only going to look at zero range from site 0 and to the left. So my zero range dynamics is the usual one, but then I have this boundary, and at rate p, a particle can go out to the boundary, and at rate q, a particle can go in from the boundary. That's going to be my process. It's a perfectly sensible process, and it has this product geometric stationary reversible distribution on side 0, -1, -2, -3, and so on and so on. Okay, so this is how you make sense out of this blocking measure for zero range. You can only do it on the half line, and this is what you have to do, and you have this right boundary. Okay, now here is the point, and many of you already know this, of course, very well. ASAP and zero range is the same thing. So here's my ASAP, and I'm going to draw your zero range from this ASAP configuration. Here's how it goes. So I have a leftmost particle in ASAP. I call it particle 0. And I'm going to say that there is one empty space between this particle and this right neighbor. This is the empty space between particle 0 and the next one. So I'm going to put one particle here at location 0 because I'm talking about particle 0. Okay. The next one is particle -1. So I'm going to enumerate them from left to right as decreasing integers from 0 down. So the next particle I call -1. So here's -1, site -1. There is no empty space to the next guy. So I'm not going to put anything here. Okay. The next particle is called -2. So at site -2, I see 3 empty spaces to its neighbor. So at site -2, I'm going to put 3 particles there. And I keep going like that. Now I didn't draw what's coming next, so we don't know what's coming here, but you imagine how it works, right? And eventually I'm going to have full of particles. So eventually I don't have any empty spaces. So eventually everything will be 0 on my left. Okay. And let's see that I do have the zero range dynamics. So let's concentrate on particle -2, which I'm going to move to the right. If I move particle -2 to the right, then after this move, -2 has 2 empty spaces. So this side has 2 particles. -1 now also has an empty space, so I have 1 particle there. And in fact, what you can see is that exactly I have the zero-range dynamics in here. So what used to be ASAP, it now turned into the zero-range dynamics and configuration. But then I still have to work out what's going to happen with this leftmost particle, and that's where the boundary comes in. So the boundary perfectly fits the definition of the leftmost particle. The leftmost particle is called particle 0. So that's side 0 here in zero range. And I have a zero range particle here because there is an empty space next to the leftmost simple exclusion particle. Now, if this guy decides to jump here, that's exactly when I have something absorbed in the boundary. And if the guy decides to go backwards, then of course something is coming out of the boundary. So exactly this half-line zero range maps into ASAP, okay, under the blocking measure. Now, the half-line zero range is countable as well, and it's irreducible. You can reach everything for everything. So this mapping, so these processes have unique station distributions as soon as I restrict ASAP to this subspace of conserved quantity. And if you have unique station distributions and the full mapping of the dynamics, that means that the station distributions must match up according to this map. And all you need to do is look at the ground state. The ground state is the most likely state where everybody is as far to the right as possible. In zero range means that everybody is absorbing the boundary. In ASAP, it means that just particles on the right and holes on the left. You write up the new probability of this state. You write up the zero range geometric probability of this state. And there you go, you have the triple product. This formula here, after just some trivial substitutions, is exactly Jacobi's triple product, the beast I showed you in the first line. So that's the proof. Okay, it's very simple. Now, this is the part we did with Ross Bowen, a student of mine before, and then later on a postdoc and a student, Dan Fretwell and Jessica J. We were looking at how to generalize, and we could generalize some of this stuff to some more models. So this is a bit newer. I'm going to show you a generic ±0 family of models. So the state space is that you can have a plus, you can have a minus, or you can have nothing on a site. So here I have 3 pluses. The following jumps can happen. Pluses can move to the right. That's a possible jump. You can create a pair of plus on the right and minus on the left out of nothing, assuming that you didn't have anything on those 2 sides. So from nothing, you can create a pair. Minus moves to the left, and then minus and plus can annihilate. So these are the jumps. This is the totally asymmetric version. So you could also do this to the left, but this was the totally asymmetric jumps. So everybody to the right only. You can also have the left jump similarly. And I claim that this is really nothing else but a 0-1-2 model, 0-1-2 particle system. So plus will mean 2 particles, empty site means 1 particle, and minus will mean 0 particles. And if I play the movie, then you'll see that it exactly is the same thing. So plus goes to the right means that a particle from 2-1 moves over, and it results in 1-2. A pair creation means that 1-1 becomes 0-2. Negative to the left means that 1-0 moves to the right. And annihilation means 2-0 becomes 1-1. That's annihilation. So it's really just a particle system on 0-1-2 sides. These were again just the right jumps. You can have the left jumps as well. And then you can lay down and you can do the same trick as before. So here is how you do it. You're going to say that, okay, I have holes on the left. So that's going to be my infinite wall of particles. Then I'm going to do something a slightly different way of standing up. I'm going to look at distances between neighboring particles. Before I looked at empty spaces, now I'm going to look at distances, which is one more. So I have distance 2 between particle number -1 and the next one. And so I'm gonna put 2 particles there. I have distance 1 between particle -2 and the next one, so that's 1 particle. I have distance 0 between -3 and -4 because they're on the same side, so I don't put anything here. I have distance 4, distance 4 between -4 and its neighbor. So that's why I have 4 there. And now comes something interesting. -5 has distance 1 to -6, so I have one particle here. -6 and -7 are on the same side, no particle there. -7 again has distance 1, so the ground state on the right, the fully occupied state on the right, is going to result in an alternative 1, 0, 1, 0 sequence on my zero range picture. So it's not exactly zero range. The rule is that you cannot allow two consecutive zeros. So you cannot have more than two particles in here, meaning that you're not allowed to have two consecutive zeros in the zero range picture. So it's not exactly zero range, it's something modified. Other than that, it's almost like a zero range process. And the ground state, so this is one of the ground states, so it's always an alternating ±1. You're going to have another ground state, which is an even ground state. So you have two ground states. I just alternating these two guys. You can see the two ground states here. That's what you will have. But other than that, the analogy still works fine. And it turns out that if you stand up this model, it's a nice model. You do have product blocking measures, but you have this constraint of no consecutive zeros. The good news is that reversible measures survive these kind of restrictions. So you do have an explicit description, more or less explicit description of the product measures. You can do everything which you wanted. And here I just list a couple of examples. You don't need to understand this, just mentioning really quick. ASAP Q1 is a model looked at by Karinci, Giardina, Reading, and Sasamoto. We can do that, and you end up with some kind of even and odd terms from Jacobi triple product if you do all this. There is a nice three-state model when you have jump rates 1 to go and jump rate 2 for annihilation, and another one for creation. It turns out to give you the square of the triple product. You have two exclusion, which is notoriously difficult in the translation invariant case, but it does have product blocking measures. And you get a new identity in here, which is a bit complicated, but something new. And you can actually generalize this to K exclusion. When you have most K particles and every jump rate is 1, you still have some nice identity. And you can even stand up zero range. You can stand up zero range to get another zero range. And if you do the program, you get the proof of the geometric sum formula, which is not very useful, but it works. Thank you very much for your attention.
Thank you, Marton. Very nice talk.
Thank you.
Yes, I got very interested in this model, in the first new model that you proposed. This model, can you consider a periodic version of this?
Why not? I don't see why not.
Because it is, in some sense, or an infinite version also, right? Because this is similar to this model of Spohn and Prahofer, I guess. Mm-hmm. That is the lines that are, it is, I forgot the name of it, the lines that go ballistically and then collide and disappear or are created in empty spaces. And this is the same, but it's a random version of that.
Can you send me a reference of that?
Yes, I will do
that. Thank you. Yeah, I mean, it's a perfectly valid member of the family of these particle systems, misanthrope. It's actually a member of misanthrope processes if you set the rates appropriately.
Thank you.
There's a question online. Milton, go ahead.
Hey, Marton. So it's nice to see that you get more of these Jacobi triple product identities. Last time there were less models, I think, right?
Well, the things we get are not so nice as before, but we still can do something.
Well, my question is the following. So usually when you have models that satisfy nice algebraic relations, they are also nice for other reasons. So do you think these models are nice to analyze better?
Yes, absolutely. So the reason Karinci, Giardina, Reading, and Sasamoto were looking at ASAP Q1, one of the reasons is that it has extremely nice duality properties. So and it's connected to various SL algebras as far as I understand. So this is definitely a nice model. This model here we use to show a very complex hydrodynamic picture because this one has a non-concave nor convex flux function with the proper parameters, but still attractive. And this one is ugly. exclusion is, if anybody looked at 2 exclusion, I think we all agree that it's ugly. We don't know the translation invariant distributions, and that's one of the big open questions. It has product blocking measures, so that's nice, but I don't know. So some of these models are indeed interesting. Some others are.
Another quick question for the 2 exclusion. Where do I find the blocking measures? Do you have a preprint about that?
Yeah. It's included in our 2018 paper with Ross Bowen.
Okay.
It's very simple. I mean, if you have 10 minutes, you sit down, you assume a reversible product blocking measure, and you find out what it is. It's okay. It's easy. You can also start with if you know misanthrope, and you know that in all of that misanthrope family, you have essentially the same product measure than zero range, then those things will be reversible if you set the parameters right, if you got city parameters right.
Okay, any more questions? Not, let's thank Martin and all the speakers in this session again. Thanks.
Thank you.